back.
Yes, I'm okay. Start.
Right. So, quick recap from where we ended off on the rule of even powers. So, we talked about this rule. I'll just explain it one more time. Basically, because it's useful. Because basically, to prove anything related to even and odd functions, again, we talked about how we can do fx. We can take an f negative x here, and then we can basically, first of all, we take fx, and we just say, well, let's simplify this. Simplify, we get something. And then we say that we take f negative x. We simplify, but we actually don't simplify. We actually take this. But remember, we plug negative x in, and we keep going until we get, what we want, right? And then we also, last step is to actually write this in some form. So k f negative x, fk neg x. So then that basically gives you your notation for f negative x. Yeah, so that's basically how that works. Um, so here, we'll just work through some of these then. All right, so first of all, let's skip question. Let's actually go to question 3, because question 3 first, because actually, no, yeah, whatever. We'll just start with question 2. So is question 2 even or odd? The cool thing is that when you don't even need to simplify, you can immediately see if it's even or odd. Just combine some terms together, and you can immediately see if it's even or odd. You don't even need to do f negative x. Oh, it's even. Yes. Why is it even? Oh,
Wow.
look. Oh, you new member, Matthew.
Hey, Matthew.
Yay, Matthew's actually here.
Yes, I just finished repertoire.
Wow, very cool.
Oh, is that the Matthew from the CS Club?
Yeah, the Matthew that yeah,
Hi.
the CP chat. All right. Because yes, the even powers rule. Perfect. Even basically, how do we get the even powers rule, right? We take at -2 and +2, you get x2 minus 4. Take these two together, we have x 4 plus 16. The reason we actually have this is, remember, because we have that x plus a times x minus a is actually x2 minus a2, right? That's just a very common thing that we see. I think you learned this in like grade 9 or 10 math, but if not, you can just take this. You see the x squared plus ax minus a cubed, which then you get x2 minus a2. And then if you do it again, you get x4 plus 16. And see, even powers rule, right? This is really important because you see the x4 is an even powers rule. So 16 is, well, it doesn't have to be even because it's x to the 0, which is even, right? X to 0 is even. And then you immediately see that this is going to be even, right? You don't even need to do anything. You don't even need to do what I did before. What about 3? Is 3 even or odd? Take a guess. This is actually easier than expect. This is like the easiest one. 3. It's the easiest one to see, not the easy one to prove, but it's definitely a lot easier than the other ones to actually look at and see. So anybody have any thoughts? Oh, odd. Is there a reason why it's odd? And yes, it's odd. The reason why it's odd, you should see this immediately, because you see +4 and -4. First of all, you see that it can be even because these two are not the same. If they're even, they have to be somewhat of the same thing, but they are not. So it's +4 -4. So you're going to assume that it's probably odd, right? It's probably going to be odd and probably not even. Right? And then the next thing you see is that you have basically 5x minus 4. So if you plug neg x in to this thing, because if you think about it, x is smaller than 0. So you plug it in, you have f5 times -x minus 4, which is just -5x plus 4, which is negative fx. Right, so f negative x. And it's also another way to see this is that, oh, you just some value, perfect. Okay, that's actually something I want to talk about. there's something called the it's called the outlier principle. This is actually really important. So the outlier principle has nothing to do with even or odd functions, but it's used in functions in general, and I want to talk about it. The outlier principle states that when you have when you have a graph, you must sub in infinite amounts of points before you can prove that graph is correct to the lines you interpolated. Because what that means is that basically if you have 2 points, what is going on with my mouse? I think it's because there's something there. All right. So if you look at this, if I have one line here and one line here, can I say that this line is going this way? Obviously not, right? Because it might go here, it might go here, it might go here. How can I say that it's going to go this way? I can only say that if every single point on this line is known. And as you can see on any graph, there are infinite points, which means that I would have to graph infinite points to figure out if that line is even or odd. Right? So that's why we can't just plug one point in and say that, oh, it's odd. Well, you can definitely say that it's not even, because if you see that one point, then it's probably odd. But you would also have to prove that all of the other points are odd. Because if you just plug one point in, we come up with the outlier principle, which we are violating that outlier principle because we only tested one point. And if you only test one point, the graph can go any way from that point, right? So the outlier principle is really important when looking at these problems because we can't just sub a value in. We can do that technically to say that, let's say it's not even or it's not odd, but we can't say that it's definitely even and definitely odd. Because we talked about this before that not all functions are even or odd. That's another thing, right? If all functions were either even or odd and you just disprove that it's even, then it's obviously odd. Right? It's like every number is even or odd, right? If you say that 2 is not odd, we know that 2 is even. You don't need to prove that 2 is even if you already proved that it's not odd. But here's different, right? Because we talked about it before in this slide that not all functions are odd, even or odd. Some of them are both, some of them are neither, which is why we need that outlier principle. The outlier principle becomes really important when not all things are A or B. Because then you come up with places where you might make a mistake if you just immediately say, oh, this is A or this is B. Yeah, I just want to explain this more clearly so then you know why it's important. And this actually comes up in anything too, even in statistics, right? In statistics, when you're taking a variable distribution, a general distribution of the numbers, you can't just verify that by saying, oh, this is 16%, this is 16%. Oh, it's definitely going to be, symmetrical, because it probably isn't, right? You don't know. This comes up in any mathematical field in which you have to plot points and interpolate the points between them, is that you need infinite number of points. All right, that was probably not more than you needed, but it's really good to know this if you're going to higher grades and learning about functions, because this is a grade 11 and 12 concept. So we're still going to try to go at the grade 11, 12 level, right? So 5x plus 4, 5x minus 4. Again, this is odd. Okay, next one. We'll just do 4 because I already talked about 5. 4 should be literally the same as 5. So just if you can get the answer right, I'll just assume that you know how to do it. Because we talked about 4 and 5. We talked about 5, so 4 should be pretty similar. Anyone want to take a guess on whether it's even or odd? Step right up to the lottery. It is a 50% chance of whether you're right or wrong. Even. Perfect. All right. So I think you did it the right way, but I'm just going to explain it anyhow. So how do we know that this is even? Well, first of all, we have to simplify it. And it's 2, 1 plus x, 1 plus 2, 1 plus x squared over 1 minus x squared. So 2, 1 plus x2 over 1 minus x2. And we say that, wow, look at this. Look at this. Look at this. Look at this. Boom. Rule of even powers. Now you might say, oh, but this is a fraction, right? Do we simplify the fraction? We don't need to. We don't need to. Because the rule of even power states that any polynomial, and and also this doesn't even need to be a polynomial, right? This just needs to be a function. It just needs to be a function, right? This is technically a polynomial, but it's just a rational function. A rational function is just a polynomial on the top and bottom. So in essence, it's still a polynomial, except you get 2. And you can think of it this way, right? Like if you have this, if you set this as fx and you set this as another function like gx, fx is even powers and gx is even powers. So when you divide them, they still all have even powers. Right? They don't disappear just because you divide them. Like if you have 3 divided by 2, this one is odd. Just because you divide it by an even number doesn't mean this one is now not odd. It's still odd, right? Like you're just dividing an odd number by an odd number. Like it's kind of like saying when you add an even number to an even number, it's still even. It doesn't change the essence of the even number. It's still even. It's just that it's just something to note. Right? So then which means that this is a very strong theorem because the theorem for even numbers, the even powers, actually works in this case, which is extremely interesting because we see how crazy this theorem is in telling us that this is just basically even. It is very cool how we can actually use theorem of even powers on rational functions that are not polynomials if you think about it, but are polynomials if you think about it even more. Because if you look at it and you're like, okay, I'm just going to plug x in, then you don't see this really cool fact, right? So sometimes if you go slower and you think about it, you get really cool things that come out of it. All right. Any questions? Take a minute. I'll take like 10 seconds and just do this. Just read this for like about a minute. I had to go do something, aka go to the washroom. So like, give me like a minute. Cool. Just read this, and if you have any questions, go ask Elaine or Shao. Give me like 30 seconds.
Okay, go. Okay, so is he in the washroom right now?
I thought you were gonna play the music.
Okay, you want it? Sure.
Okay.
Okay, just kidding, just kidding. Who? Oh, the Jerry, the person who just speak, is left. Like go to the washroom.
Yeah, he went to the
Yeah.
washroom.
Do you have any questions like for us or for like any you have any plans for like contest? Not really. Okay.
Do you have any good suggestions about what should we teach next week? Do you want to learn anything?
What did you guys say about me?
We just say that you're super good, super nice.
Yeah.
I think that's not the case. Not really. Doesn't mind. What did you say about me?
Yeah, so basically I say you're not good, and then Stefan said not really.
No,
And I
he said you're not good. I was like, what do you think? And then-
just
no,
kidding,
no,
just
we
kidding.
didn't. Just kidding.
It's okay. Yeah. You always have the right to bully Jerry.
Mhm.
Wow. Okay, that's not very nice, Shao. Guys, Shao's actually really mean. Okay. Anyhow.
Yeah, I
Cool.
am.
So let's move. All right. Do you have any questions? Before we move on.
No question.
Cool. Let's move on to the not as easy problems. Now, these ones, I wouldn't say are not as easy. They're just, you need to think more. Now, I'm extremely bad at thinking, so I wouldn't know how to solve these, but fortunately you do. Yeah. Right. Cool. So we'll just start from 11 and just put in the chat when you have the answer. This one is a bit more tricky, and we're gonna actually look at function combination. I'm actually might even open up a Desmos window just to show you what it looks like. Uh, how do you, oh, you can exit full screen. All right. Okay, what is this? This is odd. 11 is odd. Is there a reason why it's odd? Steven, do you want to give a really quick explanation for why it's odd? It is odd, but do you know why? Or was that just a guess? Oh, okay, great. Yeah, perfect. All right, so the trick here is that it's kind of hard to use negative, but you see basically immediately this is obviously odd because like Steven said, you can just use absolute value x. I mean, there's no one else here, so who am I even explaining this to? But but the absolute value of negative x is equal to the absolute value of x, which is just equal to x, which is also equal to the absolute value of x. So yeah, that's how you do 11. I wanted to show you what the absolute value function actually looks like, but my computer is very cooperative and definitely doesn't refuse to do anything. All right. So if you go to Desmos, and first of all, we're just going to look at what the absolute value function looks like because it's actually cooler than what you think. This is the absolute value function, and the reason the absolute value function is the regular one is odd is because, well, I mean, the absolute value in essence itself is even, right? This is even itself, right? Because if you see that this one maps up to this one on the right side, so like if I just let y equal to 3, you can see that these two match up perfectly, right? And actually, and also what you can actually do is you can actually move this guy. No, Elaine, what are you doing? All right. Wait, Elaine, do you need something? If you need me to do something, I can. If you just request remote access to troll, then no. All right. So basically, as you move this up, you see that this is basically what an even function looks like. And then you say that, oh, look, what if I can do something even cooler? And then you're like, okay, so what if I actually graph out that function? Right? And the reason for that is because when you divide an absolute value by x, you actually push it down. This one becomes negative because x is negative, and this one becomes positive because x is positive. So now you see how cool this is. You see that? You can actually check this by graphing the function. It's just a trick I wanted to show you because it's really easy to check your work, and also you learn about how to graph functions because this is also something we're going to touch on, how to visually think of how functions work. All right. 12. 12 should be easy. I probably won't just ask you. You can just say if it's even or odd. All right, 12. 12, not sure. Okay, okay. So let's see. Okay. Do you want to give a guess? Or why are you not sure? Odd. Okay, cool. So first we're going to look back at the question. We see, well, okay, first of all, we see that if it's even. Well, let's simplify this first, right? X cubed minus 1 over x minus 1. Can we simplify this? The answer to the question is yes, but also no. The pitfall that most people often come into is that they see this and they're like, okay, x cubed minus 1. Let's factor out the x minus 1. Let's factor out the x minus 1. We have x squared plus x plus 1. And then, but then you're like, well, what do I do now? Like that kind of got us nowhere from the original point, right? Because if it's already a polynomial, two polynomials, there's no point to put into another polynomial because it's already one. It's like saying, I have a really complicated equation, but I can already deal with it. Why would I not, right? So then the second question is, what do we do if we don't simplify it, right? So first of all, we want to disprove that it's even or odd. And the way we disprove that is that if you think about it, we can actually do what Steven said, right? Because this doesn't look even or odd. Like if we can actually simplify it, we can actually see that this doesn't look even or odd, right? This is like a squared plus x plus 1. It would look something like this. It wouldn't be on the x-axis. So we think that it's probably not even or odd, but we had to prove it. So how do we prove it? Well, we actually talked about this when we talked about proofs, but the coolest part, the fundamental part, is that you can prove by disproving. We can actually use the outlier principle. You might think the outlier principle is just so that, oh, I don't make a mistake on the test, but no, the outlier principle can actually be used to our advantage. Because now, instead of proving that something is even or odd, we're actually proving that it's not even or odd. So now, instead of before where we're saying, oh, the outlier principle is so that we don't accidentally say that everything is even or odd because we only test one point, we don't know if all the points work. Here, if you think about it, if I find one point and I prove that it's not even or odd, then for the whole graph, it's not going to be even or odd, right? That's basically the essence of the outlier principle. before the essence of the outlier principle is that if you only know one point, you can't know if it's even or odd. But if you know one point, you also can for sure know if it is even or odd, if there's a possibility of it being even or odd. Because imagine if I have this. Imagine I have something here and something here. Is this graph going to be even or odd? It's definitely going to be neither. I don't care how this looks. This might mirror this perfectly. But there will be some point where this will not match up. So as long as I have any point or part of the graph that's not even or odd, I'm done. So how can this help us at all? First of all, it can help us because we don't need to simplify. But second of all, what if we just take a random point? Someone give me a random number. Random number. 7, sure. Uh, because the number is really big and I don't want to calculate 7 cubed because I'm a boring person, I'm just going to choose 2 because I can calculate 2 cubed without accidentally saying 9 like I accidentally write on tests. I actually did this once. Like I went like, oh, 2 squared. What is this? 2 cubed. What is this? Oh, this is just 9, right? Don't ask how I did that. That was very smart of me. Don't question. Anyhow, so 2 cubed. So F2 is equal to 2 cubed minus 1, 7. No, wait, 8 over 1, it's just 8, I think. No, it's 7. I'm very smart again. I'm very good at basic arithmetic, as you can see. But if you take f negative 2, negative 2 cubed is negative 8 minus 1 is negative 9 over negative 3, which is negative 3. So if I take any random point and I say that this will not possibly match up, is this odd, even, or neither now? Is this odd, even, or neither? What is the neither? Perfect. It is neither, right? Because we use the outlier principle to our advantage. So next time, if you think of a principle that's actually used to disprove your argument, it can also be used to reverse prove your argument, right? Because if you think about it, a disproof is just not proof. This is a cool thing to just mean negative, but in mathematical notation, like in like the biggest mathematical principles, which are set principles, we don't actually use the negative sign. We use this, which means not. So like A equals to not B. But basically what this means is that if you think about it, a proof and a disproof. Actually, this is actually proof. I'm very good at writing. A proof and a disproof are actually very similar. I cannot do anything today. Proof, like if you think about it, it's just a negative of proof, right? So we use the outlier principle to disprove our argument. Now we're using it to prove our argument. Any questions? So basically we just found one point that works. All right, if there are no other questions, we'll move on to 13. 13 is kind of tricky, so I want you to think about it for a few seconds. Where's the thing? Both. Why would you say that? Why is it both? I wonder why. Okay, so let's look at why. Oh wait, did you maybe even? I'm not sure either. Let's look at how this works, and then we can have a uh, possible discourse for how this works. Right. So first of all, we have x4 equals to y4. Now what we actually have is that we have some kind of equation. Let's look at an easier one, right? Whenever we have a harder one, we always want to look at an easier one. Simplify, simplify, simplify. Even the problem, right? If you see a hard problem, make it easier, find a pattern, and then extend. So you have x squared equals to y squared. Let's look at this one. What are the solutions to this equation? Also, remember this is actually fx. So like x squared equals to y squared is like the solution to this equation. So basically, what this means is that you actually have two solutions, right? You have x equals to absolute value of y. And if we actually look at this, we see kind of the same thing. But here's a problem, right? We can do this the same way as do x to equal to x squared equals to y squared, but we actually encounter a problem. To take care of this problem, let's actually, again, graph it. Because it's really important that we especially graph this one, because this is the one that's really, really tricky. If you don't actually graph this perfectly, you're going to just treat it like x squared equals to y squared. But it's actually not. It's actually much more complicated. It's more complicated because you don't actually see that. Now you might be really confused, right? Because a lot of people think that x4 equals y4 is almost the same thing as x cubed 2 equals y2. But that's actually not true. Because if you think about it, x4 equals y squared is the combination of f equals to x and f equals negative x. Because how this function composition works is that you have x equals, so if you think about it, you have x equals to y. If I take x equals to y and I for both sides, I get x4 equals y4, okay? If I have negative x equals to y and I for both sides, I have x4 equals to y4. So actually, I have 4 different branches coming out from the same thing. The problem is I cannot see where my thing is coming up, but you get the point, right? It's actually 4 different equations. It's actually plus minus x equals to plus minus y. This is a theorem. You can memorize it, obviously, but you can also derive it. It's kind of like the outlier principle. You need to be able to do it even if you don't know it. Like here, you can say that if I have x4 equals to y4, well, let's just simplify and I get plus minus x equals to plus minus y. You can do that, no problem. But if you don't know that, you can also derive it, because if you think about it, it comes from 4 different equations. This one is x equals to y. This one is x equals to negative y. What am I doing? X equals to y, x equals negative y. I cannot click on this. What is going on? Okay, whatever. X equals negative y, negative x equals negative y, and negative x equals y. Get it? Yeah, just like Elaine said, is it a function? It's not even a function, because if we run the vertical line test, nope, that's not the vertical line test. That is the horizontal line test. You can see I'm not drunk. If you apply that, you see that it actually hits 2 points. Oh no, it hits 2 points. So it's not even a function. And the reason that it's not a function is because 4 different, that was Google Classroom, 4 different points actually lead up to it. 4 of them. That's insane, right? And it's really hard to see that if you're just noticing it and being like, okay, here's, x squared equals y squared. Let's just brute force it. So now that we know that, we can say that is this neither or both? Well, this is actually neither, because it's not even a function. An even or odd function needs the basis that it's at least a function. This is not even a function, because you have to write it as plus minus y equals to plus minus x. And if you do that, you get plus minus fx equals to plus minus x. This isn't a function, right? Functions are written as fx equals to k. You can't just write, plus minus fx equals something. That doesn't make sense. That doesn't make sense at all. So we can't even do that, right? That's not even a function. All right, last two, 14 and 15. So if you're ever, stuck on stuff, just search it up. Right. 14 and 15. Now, 14 and 15 are also kind of tricky because there are restrictions. I point these out every time because a lot of people just miss them and they just miss them. So make sure to not miss these restrictions, because these restrictions are important if you're considering these solutions or whether it's even or odd. So 14, is it even or odd? Even or odd? Even or odd? Even or odd? It can also be neither or both true, yeah. Oh, Shao, did you know you can also save chat? You go on the right side and you do save chat. can say all the message in chat. I don't know why. You can just do it.
Wait, are
Why
you
not?
talking to me?
Oh, yeah, it was just something I noticed. Okay, never mind.
What? Wait, what?
Oh, I just noticed that you can save the chat, which was kind of funny. Okay, anyhow.
I don't think so, cause I'm doing the video right
Yeah,
now.
I know. I don't need you to. I'm just saying it's something that exists. And it's
Oh wow,
yeah,
cool.
that was what I meant. All right. So even. Even. Why is it even? So let's okay, is it even? Maybe. Let's consider the solutions again. Right, so x cubed x squared plus y squared equals 0. And then we say that y squared equals to negative x squared. So, or y equals to root plus minus root negative x squared. Right, so we're going to basically do that. Push the root like this. Now there's something you see, and there's something I see too, is that x squared, is that it's a trivial inequality. Does anybody know what the trivial inequality is? You forgot the plus minus root. Yes, that is very important. Do not forget the plus minus root. Every equation has a plus minus and also square root. Right, don't forget the plus minus. If you have squared, if you have 4, both sides are plus minus. If you have 2, only one side. Think of it as, what I like to do is I like to do 2, 4. That's how I remember it. So 2 and then 4. 4 means both of them. 2 means one of them. So you see that the trivial inequality, does anybody know what the trivial inequality is? If you don't know, it's fine. Basically, trivial inequality means that x squared is greater or equal to 0. That's trivial inequality. And then you're like, well, what can I do with it? Well, you see that, but this is 0 though. Like if I said x equals to 1, this is like 1 squared negative, then it's a negative number. I can't square root a negative number. Well, you can, but it says over the real numbers, right? So if you take the negative of like, if you take negative 1 square root, you can do that. Like you can get I, but that doesn't get you anything. Right? And same thing if you get any bigger number. If you get negative k roots, you just get root ki. Now that doesn't get you over the real numbers. To make it under the real numbers, we have to restrict x's domain to x equals to 0. So if you think about it, fx is just equal to 0. Right? Because no other number works if I can't get 1, because x has to be 0. X is greater or equal to 0, but then I see here is that x also has to be less than or equal to 0 because it's a square root of a negative number. So then the only possible explanation is that x is equal to 0. Right? So fx is just 0. And if fx is 0, it is both. Because again, if we graph it, it's just a line. A line is both even and odd, right? Because if you flip even, it's still odd. If you flip odd to even, it's still the same. So they're both even and odd. So both, yeah, exactly. All right, that's really cool. Let's see how much time we have. If I need to stretch out anything. Yeah, we're gonna stretch out 30 seconds and talk about nothing in particular. I'm joking. Just end like 30 minutes, 30 seconds early. All right, so last question. X squared plus y squared equals 1 with y greater than or equal to 0. This is pretty cool. It's cooler than the other ones because I actually wanted to talk about one of the applications of these questions. And I want to talk about how they're useful in functions, because if we have time. What is this? So x squared plus y squared equals 1. Again, take a guess. If you don't, if you want to, if you try it, go ahead. If you don't, you can just guess 50%, or actually no, it's 25% chance now, but still a pretty high chance you can get it right. So yeah, that is that. Even. Okay. Okay. Cool. Why is it even? The reason why it's even? Okay. Just kind of guess. Cool. Okay. That is a very good guess. Very good guess. And you're definitely right because the even powers actually work for y too. It works. It works, yes, but that's not, you're not supposed to apply it like that, but it works. It's a coincidence. It's not like the outlier principle in which the coincidence bad. It's just a complete coincidence. Yeah, half guess. Yeah, basically the um, even powers signify that it should be even, but you don't completely know because like y is there, but since you see even power, you can probably guess. And you're right, it does apply to y, but not for the reasons you think. It's complete coincidence. You can't actually apply the theorem of even powers to y just randomly because it might not work. But for this one, it definitely works because x in this case x is squared, so what y is actually doesn't matter, and also y is greater than 0. First of all, do you know what the equation of this actually is? If you don't know, we're going to graph it. That is, exit full screen and let's graph it. Right. Again, if we don't know, we'll just graph it. X squared plus y squared equals to 1. It is a circle. Ooh, ooh, it is a circle. It's so cool. And the reason that it's a circle because it's a parametric equation, which we'll also get into. But for now, the reason that it's actually a circle is that you have these, is that basically you have an xy value. It's a parametric. As you can see, these values, how do I can't zoom into the values because they're just the same size. This is not a very use, it's not a very good software. All right. Yeah. All right. So what this means that it's basically, as you can see, these numbers are changing really fast and they're not real whole numbers. This is actually a trigonometric function. So it's a parametric function based on sine and cosine, which means that which means that it's actually symmetrical. But even if you didn't know this, you could probably guess that it's symmetrical because if you know that it's a circle, great. But if you don't know it's a circle, this is just to show you that any kind of parametric equation like a circle where you have x to the something plus y to something equals the some number is always even or odd unless otherwise stated, because sometimes you have things that are shifted, but in most cases these are even or odd based on their structure and general ability. Oh, you use the fx equals f negative x formula. Yeah, but how would I do that? This is x squared plus y squared equals 1. I don't even have fx yet, right? So how would I use that formula? So next we're going to figure out how to do it if we use the fx equals negative x formula and we don't even know what this is. First of all, y greater equal to 0, which means that we're only looking from the values from here to here. I don't even know if I can do this. And then y greater equal to 0. So which means that we're actually only looking at these points, so above here, not below. Right, so that's really important distinction. This is actually called restricting the domain. Restricting the domain is when you take a subset of the integers above or below the axis instead of just taking all of the numbers, because sometimes it's not a function. So first of all, how do we do this? Well, first of all, we have to restrict the domain, right? So we restrict the domain and then we can do the work. So we get y. This is kind of like how we did inverses, remember? So we take y squared equals to 1 minus x squared. We want to take the y squared on one side, and then while we have the y squared on one side, all we do, we throw it. We throw it out. We square root both sides. So y equals to plus minus, don't forget that, root 1 minus x squared. Now you might be thinking, how do I deal with this? It's a plus minus. This isn't even a function. It's not. But look, y is greater or equal to 0. So now this is actually equal to square root 1 minus x squared. Because you can't have negatives, right? This is basically gone because y is greater or equal to 0. Always look for the restrictions because the restrictions will help you out, either make the problem easier or make the problem solvable. If a problem looks impossible or looks really weird, look for the restrictions because there are almost always restrictions that make the problem possible. Y is positive. Yeah, or 0. So basically make it positive. And now you say that, well, this is basically a continuous function. It always has a value, which means that if we plug negative x in, oh, and then now we can use the theorem of even powers again, and we can now say that because we have even powers here, this is again, square root is just like a polynomial. It's just like the icing on the polynomial. This x squared is even powers, so we could say by the rule of even powers, because the negative is now gone, only it is a function and it is even, and that is the answer. And we did that by doing something cool called restricting the domain, and you're going to see that a lot more in combination math and in curriculum math, because you're always going to have to restrict the domain and range to some value which you can calculate. All right. So last part, and that's basically all I have for today. So here are the final things. Yeah, it's really cool stuff. So here is everything, all the answers to the questions, and yeah, I think that's all for today. If you have any questions, feel free to ask any of us now, and I'll end in a few minutes. And here's just one more thing I wrote, which I wanted to outline or highlight, which is that if I do not like this. Okay. So basically, if AB is a solution, then negative AB will also be a solution. That's all we need to show that the function is even. Meaning that if all we need to show is that fx equals to f negative x. Right? So if we can show that any point AB must map to any point negative AB, then we're done. Right? So we basically show this mapping. It's kind of like the mapping rule of xy, like xy to fx y. But instead of doing that, you basically now map xy to negative xy. So it's just a different mapping rule from what you learned from transforming functions or doing functional equations, but kind of the same thing. When I say kind of the same thing, I mean roughly the same thing. It's definitely not the same thing entirely. There are a lot more tricks or loopholes to this, but we mostly went through all of these loopholes. So you should be pretty familiar with doing them now. If you have any questions, feel free to ask again. We'll end in a few minutes. Yeah, we'll end in like 30 seconds. So any last questions before we end for today? The meeting is over. Yes, it's 4:30, which should signify the end of the meeting, unless you have any other questions, which we will stay for. But if not, then yeah. Okay, yeah, have a nice day. Thank you so much for
Have a
coming.
nice
Bye.
day.
Bye.
Bye.